Welcome to Massive Open Online course on Basic Principles and Calculations in Chemical Engineering. We are discussing about that basic principles based on material balance and energy balance equation. So, in the previous lecture we have discussed about the energy balance with multiple streams without reactions, and also the analysis of this kind of energy balance equation based on the examples on evaporator, dryer, distillation column, etc. So, in this lecture we will try to again discuss about that energy balance with heat of reaction. So, in this lecture we will discuss the heat of formation, standard heat of reaction, and also how to analyze those standard heat of reaction based on the heat of formation, and also with some examples. Now, you have to know what is that standard heat of formation, because one of the important aspect of energy balance when reactions will be involving in a particular process. So, for that you have to know that how that chemical compounds to be formed, and during that formation what will be the energy released, or what will be the energy required to form that particular compound. Now, that will be actually regarded as standard heat of formation, and here standard means at a standard temperature and pressure what will be the heat is actually required to form that particular compound. It is called standard heat of formation. Now, this standard heat of formation you can actually estimate based on the enthalpy or energy required for a particular reaction, and by which that reaction is carried out, and in that case the heat of formation of each individual constituent that take part for that reaction at a particular operating condition, if you know that enthalpy released or energy changes caused by that reaction, then you can find out what should be the formation of that particular condition, like if it is at a standard temperature and pressure, then it will be called a standard condition. So, at that standard condition what will be the energy required to form that particular constituents which are actually taking place, which are actually participate for that particular reaction. If I consider that there will be a certain change of enthalpy due to the temperature change, so that will be regarded as sensible heat. So, if you know that sensible heat for that particular enthalpy change, and if you know that heat of reaction for that particular reaction, then from that heat of reaction, if you subtract that sensible heat, you will get that heat of formation of that constituent. So, here in this slide it is shown that here that heat of formation of any constituent which will be denoted by that delta H Fi0 hat. Here see that this hat is basically that specific heat formation, and the 0 here denotes the standard condition, F for formation, I for constituents or that species there. So, delta H hat 0 Fi, it is basically that standard heat of formation of constituent I, but at the specific condition, that is a standard condition, and also at a specific terms like per unit mass or per unit mole, what should be that energy required or energy released for that formation of that constituent. Now, this delta Hi, if I consider that the it is the heat released or absorbed by that chemical reaction there, then we can have this standard heat of formation just by subtracting this enthalpy change, or you can say that sensible heat change by the change of temperature from its standard condition if is there, then you have to subtract this. So, from this subtraction of this energy from this heat of reaction, you can easily calculate what will be the heat of formation there. So, to find out that heat of formation, basically you need first to allow a reaction and then measure the heat of reaction that is released, that should be find out experimentally. So, from that experimental value, then you can find out what should be the heat of formation by this equation. And in this case, if you are saying you are seeing that is there any phase change there, then you have to include all that enthalpy change because of that phase change. So, that is heat of vaporization, heat of sublimation, heat of melting. So, all those terms to be included also if there is a phase change there. If there is no phase change, then you have to easily omit those terms there. Now, basically how you will define that standard heat of formation. So, it is basically defined as the enthalpy changes which is associated with the formation of 1 mole of the compound at 25 degrees Celsius and 1 atmospheric condition. This is called standard condition from its element constituents as they are normally found in nature, like carbon, oxygen, nitrogen, hydrogen. They are most important element constituents which are naturally occurred. Now, the heat of formations to be 0 in this standard state for each element of this carbon, oxygen, nitrogen, hydrogen at 25 degrees Celsius and 1 atmosphere. So, which constituents are naturally occurring substituents or constituents, those heat of formation to be regarded as 0. Whereas, if any chemical compound is formed based on some other element, then you have to consider what should be the heat of formation for that particular compound. We will do some example for this understanding. Now, before going to that, also you have to know at a standard condition what should be the heat of reaction and how to estimate that heat of reaction from the standard heat of formation there. The standard heat of reaction is calculated as the difference between the product and reactants enthalpies, or you can say that heat of formation when both reactants and products are at standard conditions, that is at 25 degrees Celsius and 1 atmosphere. Now, suppose there is a reaction like here AA plus BB, which will give you the products of C and D. With this that stoichiometric coefficient as shown the reaction equation here in the slide. So, in this case you can find out the heat of reaction at this standard condition by this expression here given in the slide, like here delta H Rxn 0. This is basically that enthalpy change or you can say that heat of reaction at a standard condition. 0 means here standard and Rxn means reaction. So, delta H Rxn 0, this is basically standard heat of reaction, and this can be calculated based on the difference of total heat of formation of the products and the total heat of formation for the reactants. So, total heat of formation for the products can be calculated by this terms here. This is basically a summation of all heat of formation of the products components. Now, here Ni is the number of ith components in the products, and here Fi, this is basically the heat of formation for that ith component. So, in the products, if there are n number of components there, so we can have this total heat of formation just by multiplying this standard heat of formation of each components by the number of that components there. And similarly, you can get that total enthalpy of formation just by multiplying that heat of formation, that is a specific heat of formation with the number of moles in reactants. Now, if we consider this reaction equation, where you will see that the reactants are A and B as given here in the slide, and products are C and D, whereas their stoichiometric coefficients are A, B, C and D. Now, in this case you will see that heat of reaction for this reaction, it will be as number of moles for products here C and D, for C and D respectively. Here then we can calculate the heat of formation for the C as C into delta HFC. This will give you the heat of formation for this components C. Similarly, heat of formation for the component D in the products, that will be your D into delta HFD, and then you have to subtract this enthalpy enthalpy of that reactants A and B as per this A into delta HF0 minus H delta HF0B here. So, what these up to this here, this is the total enthalpy of formation for these products, and this is basically the total enthalpy for that reactants for the formation at that standard condition. So, just by subtracting this total heat of formation of the reactants from the products, you can get that heat of reaction at standard condition. In this regard, if you have more than one reaction, then you have to apply Hess laws. According to Hess law, it is basically if a set of reactions can be manipulated through a series of algebraic operations which will give you the desired reaction, then the desired heat of reaction accordingly can be obtained by performing the same algebraic operations on the heats of reaction of the manipulated set of reactions. That means, here if you have more than one reactions like reaction 1, reaction 2, reaction 3, reaction 4 like this, and if you are having the respective heat of reactions like heat of reaction 1, heat of reaction 2, heat of reaction 3, heat of reaction 4 and so on, then you can find out the the total or desired heat of reaction just by manipulating by the heat of reaction by subtracting those or either one from another one in this way. So, this is called Hess law. Let us do an example first giving only one reaction. This is not Hess law, as per that from the standard heat of reaction, how to calculate the standard heat of reaction. In this example, it is given, calculate here the standard heat of reaction for the following reaction given, where this reaction ammonia is reacting with oxygen, which will give you that nitrous oxide with water. Now, in this case 4 gram mole of ammonia is participating to react with oxygen to give the production of nitrous oxide and that water. In this case heat of formation at a standard condition in kilocalorie per gram mole is given as for ammonia minus 11.04, for oxygen it is given 0, for nitrous oxide it is given 21.60 and for water it is given minus 57.80. Now, as for that heat of reaction according to that principles of finding out the heat of reaction from the heat of formation. So, we can find out what should be the heat of formation for this product side. It is basically here, since the product side is nitrous oxide and water. So, here 4 moles of nitrous oxide that will require require that heat of formation is per mole it is 21.60. So, for 4 moles it will be 4 into 21.60. Similarly, for for water, it is given per mole that heat of formation is minus 57.80. Then what should be the total heat of formation for 6 moles of water? It will be 6 into minus 57.80. This is for simply product side. Similarly, in the reactant side, this ammonia, 4 moles of ammonia, there, since it is naturally occurring. So, we can say that since oxygen is as naturally occurring. So, for that the heat of formation for naturally occurring compound, it will be 0. So, we can say right here 5 into 0, that will be your heat of formation for this oxygen. Whereas, for ammonia, 4 moles of ammonia, heat of formation will be equal to 4 into minus 11.04, as per mole of ammonia formation it is required minus 11.04 kilocalorie heat. So, after simplification, we can say that the heat of reaction, just by subtracting this product side to the reactant side. So, here we can get this amount minus 216.24 kilocalorie per 4 gram mole of ammonia. So, in this way we can calculate the standard heat of reaction from the standard heat of formation. Let us do another example here to calculate the standard heat of reaction from the standard heats of formation. Now, in this case, if you consider that a production of metallic manganese, there are 10 kg of manganese oxide are heated in an electric furnace with 3 kg of amorphous carbon, that is coke. In this case, it will give you the results as a products which will contain 4.8 kg of manganese metal and 2.6 kg of manganese oxide as a slag. The remainder of that products consists of here unconverted charge of that manganese and carbon monoxide gas, which is actually produced during that heating, or there is a combustion of that manganese oxide with that carbon. Then carbon will be producing carbon monoxide, which will be oxidized based on that oxidation process in the furnace. And then according to this problem, at a standard condition, there you will see that what should be the standard heat of reaction of this process for the entire furnace charge you have to calculate. In this case, it is given that 0.0413 kg mole of manganese oxide used for the production of 1 mole of manganese and 1 mole of manganese oxide. As a data, we can say that heats of formations at standard conditions are required. It is given here. The standard heat of formation for this manganese oxide, it is given minus 331.4 kilocalorie per gram mole. Similarly, other heat of formations for manganese oxide, manganese, carbon monoxide and coke are given here in the slides. And based on this heat of formation of all those components, you have to calculate what should be the heat of reaction for this whole processes. Now, in this case basis, we can consider that since here 10 kg of manganese oxide and 3 kg coke is used for this production of different components of that manganese oxide, even carbon monoxide there. So, you have to first convert this in unit which will be consistent in all cases. Now, since it is given in terms of mole, here in this case for heats of formation at standard condition, but your charge is given in kg. So, you have to convert it to moles first. So, initial amount of manganese oxide in it is given in kg, that is 10 kg it is given. So, you have to convert it to moles or kg moles just by dividing this 10 kg by its molecular weight. So, it is coming as 0.0437 kg mole. Initial amount of carbon, it is 3 kg, then after conversion or it will be as 0.25 kg mole just by dividing its molecular weight. And then manganese formed, it is 4.8 kg, you will get 0.0874 kg mole just by dividing its molecular weight. Similarly, manganese oxide form, it will be 0.036 kg mole. Now, these are the components which are formed from this manganese oxide. You will see that there will be no 100% conversion of this manganese oxide. There will be some unconverted manganese oxide to be remained in that furnace. So, what is that unconverted manganese oxide? Since this 1 mole of manganese and manganese oxide formed as like this here, this amount and this amount, that is 0.0874 and 0.036 mole there. So, for that this 0.0413 kg moles of manganese oxide is required, whereas the manganese oxide supplied as here 0.0437 kg mole. So, what will be the unconverted manganese oxide there? Just subtracting it, you will get that 0.0024 kg mole. Now, for this oxygen of this manganese oxide which is associated with that carbon to give you that carbon monoxide which will be coming out from that furnace can be calculated by this. What will be that? That will be 4 into 0.0413 here. 4 means here 4 moles of oxygen is required for that 1 mole of that manganese oxide conversion, and then you can say that 4 into 0.0413 and then minus here what will be the manganese oxide form, and here from that you can subtract this amount, then what will be the oxygen for that manganese oxide actually is required to oxidize that carbon to carbon monoxide. So, here please correct it here 0.1286 kg, it will be kg mole, and since you know that 0.0366 kg mole of oxygen is as manganese oxide. So, we can say that this amount will be subtracted from this total amount of that manganese oxide and remaining amount will be used for conversion of carbon to carbon monoxide. Carbon monoxide form, that will be is equal to then 0.1286 kg mole based on that amount of oxidized oxygen, and carbon unconverted, it will be simply subtracting this conversion of carbon monoxide to that supplied carbon there. So, it will be 0.1214 kg mole. Now, as per that material balance of the process, we can write this amount of material is supplied or entering to that furnace, that is manganese oxide 10 kg, carbon is 3 kg, whereas materials that are leaving, it will be as manganese is 4.8 kg, manganese oxide 2.6 kg, manganese oxide here 0.55 kg, carbon monoxide 3.60 kg, whereas carbon will be 1.45. So, this will be leaving from that furnace, or you can say these are at the outlet stream of that process unit. Now, heats of formation of that reactants, simply here what will be that manganese oxide, this is your heat of formation of this reactant of manganese oxide, and similarly heat of heat of formation of this coke, it will be this amount. So, total heat of formation for this reactants, it will be your minus 13.352 13,352.6 kilocalorie, and heats of formation of that products, then this manganese oxide, it will be 3367.2 kilocalorie, and then carbon monoxide, it will be that 3397.1 kilocalorie, and manganese is 0. So, finally, total heat of formation for this product side, it will be minus 6764.3 kilocalorie. Now, as per that equation of that standard heat of reaction, from that heat of formation of that products and reactants, you can get this value of 6588.3 kilocalorie after substitution of the values of that heat of formation for the products and the reactants there. So, in this way you can calculate heat of reaction from the heat of formation of the constituents. Now, example based on Hess law, let us do this example here. In this case, you have to calculate heat of reaction for this C2H6 from the following reactions. Here you will see that this first reaction, that heat of standard heat of reaction for this first reaction is given to you, and the standard heat of reaction for the second reaction, it is given to you. Similarly, for third reaction, this heat of reaction is given to you. Now, based on this reaction 1, 2 and 3, you have to calculate the heat of reaction for this ethylene to form this products of this here along with this water, carbon dioxide and this. So, in this case we can manipulate this reaction just by subtracting, and accordingly that heat of reactions just by adding, subtracting according to that Hess law. So, here also we can do the same fashion based on that Hess law, that subtracting the second reaction from the first reaction on 1 mole basis, then we can have this here, just subtracting this equation from this first equation, then we can get this. So, here whenever you are subtracting this equation, accordingly you have to subtract that heat of reaction also. So, finally, we can get this here for this subtraction. Again, this resulting reaction is to be added with the third one. This is by convention. You have to think about how to do this to get this final equation for this ethane for conversion. Now, in this case you will see that again if you add this third reaction with this resulting reaction, then you can have this final reaction as C2H6 plus 3.5 O2 which will give you that carbon dioxide and water, and accordingly then you have to add this that is heat of reaction, and finally you can get this this heat of reaction like this. So, it is coming as 1558.3 kilojoule. Now, accordingly heat of combustion of this C2H6, then it will be minus 1558.3 kilojoule. So, here from this lecture we understood that what is the heat of formation, how heat of formation can be calculated based on the heat of reaction which is obtained experimentally, and also from this heat of formation how to calculate that heat of reaction, whether it is single reaction or your multiple reaction. Now, for the multiple reaction by Hess law you can manipulate these reactions, along with that heat of reactions just by manipulating according to your problem and also convenience, and then finally you can get that total heat of reaction based on this heat of formation at a particular condition. In this lecture we have described only at a standard condition. In the next lecture onward, we will try to give some other examples which are actually not in standard condition. There will be a that heat of reaction at a certain condition, where you can get that there will be a change of enthalpy because of that temperature change, as well as you will see that there will be a enthalpy change because of phase change, and based on that enthalpy change due to that temperature effect and also phase transformation, how that heat of reaction can be calculated at a particular operating conditions. So, we will be discussing all those things in the next lecture. Thank you.